So in previous class, we discussed a similar graph, but for lasso regression, which I copied from the Tipsy book. So there, like all the coefficients, so this is a plot of coefficients and x-axis is the lambda parameter, or you can have some equivalent parameterization. And the idea is that for ridge regression, you can see that as lambda increases, all of them goes to zero and all of them goes to zero kind of together.
Hmm.
Like nobody is reaching zero early and other guy is reaching zero late. Whereas in case of lasso, some of them were reaching zero early and some of them were reaching zero very late.
Mhm.
So that's what the lasso is like kind of doing variable selection for us in that manner, whereas ridge is never going to do that.
Got
All
it.
of the parameters are synced, but in kind of parallel manner.
Okay. Okay. That's interesting.
That's like, yeah, that's the main distinction you should remember about ridge versus lasso.
Hmm. Sorry.
And the other thing I would mention quickly is that so all the graphs you see that for the left part, it's kind of flat, right? You
Yeah.
just, no, for the right graph itself, right plot. So anything for lambda less than say 10 power minus 1,
Yeah.
that part is mostly flat. So that means if your choice of lambda is very small, then it's not going to affect in any way at all.
That's what okay, I can see that. I'm forgetting a little bit though here, Sujay. It's not affecting what? What is my coefficient value here? What does this
So
mean?
the theta hat or
Theta.
beta hat, whatever.
Okay, got it,
Yeah.
got it, got it. That's what we're trying
Yeah.
to optimize for.
Theta
Okay.
is not affected. So if your lambda is small, then it's not affected by theta. It's not affecting the theta at all.
Okay. 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 So where do we want our lambda to be kind of like right at the bottom, like as it's flattening out then? Is that our goal?
Kind of that, but it might be little bit left or right of that,
Okay.
subject to what the cross validation results are saying.
Got it.
But
Okay.
that is like the ball. If you don't know where to do the cross validation, like let's say, like when you do this kind of thing, it also costs in terms of computation, how many lambdas you will playing with, right? So this will tell you the ballpark around which you should choose your test lambdas.
Got it. Okay. Okay. Okay.
Yeah, so all this is fine. We have okay, yeah, and then he has derived some nice formulas. I think
Yes, this was the
the
formula
bias
that
variance,
we wrote on the board as well too. So that's the big one.
the bias variance
Bias
decomposition.
variance trade-off. Yeah, exactly. So we call, oh, bias variance decomposition. Nice. Okay.
Yes.
Okay. So that's this lecture here.
Okay, that's all.
One question I had that was coming up during our study session that all the students didn't understand was the difference between that noise term and then the error as well too. So I guess I'm confused on when we have,
Remind me, what are you referring to here?
so we have this Z, which we're calling unknown noise,
Yes,
right?
good.
Versus like, what does the error give you in the function of like the actual value versus the data set value? Like that difference?
Yeah, that's a good question. So let's understand two different things. Okay. So there are different kinds of data in this world. Some data is where you choose an X and then perform some experiment and you observe some Y. And there are some other kind of data where all the data is given to you. So nothing is designed by you. Like some study was done or some event were done, some clinical trial in medical science was done, and all the data is just given to you. You don't get to choose anything anymore.
Okay.
So in the first case where you are choosing an X and running the experiment and finding the Y, so those are like called designed kind of experiment.
Okay.
So let's say you are trying to optimize some machine in terms of what is giving me the best performance in some metric or something.
Okay.
And then you are doing regression to understand the behavior of input versus output relationship.
Yeah.
So in those cases, just think of it this way that I chose my X and then the output depends on X, but also some other source of like there are some like Z1, Z2 or some other variables you can think of. There are some other sources of sources of inputs which is beyond my control. For example, in case of manufacturing, it can be the person who is running it on a given day. You
Oh,
don't have any control of that. Okay. So these are
gotcha.
like, we would say that the sources of noise or sources of variability that are beyond our control.
Okay.
And we are never going to get a full list of those things. So we never be able to like fully understand what is the reason for that. So statistically, we are like assuming it's a unknown but normal or whatever distribution. Okay.
That makes so much sense. So we try to define it with a certain set of parameters that I
Yes.
like your student score example, right? Like amount of time studied, previous exam scores, blah,
Yes.
blah, blah.
Yeah, yeah,
But
something like that.
but then there might be
There
some
might be some other,
variability.
yeah. So it might be that okay. So on that particular day, the room temperature was unusually high or something. So all
Yeah.
students were affected by that. Like that is
Yeah.
never, you're never going to get that data with you.
Got it. Got it.
So there are unknown sources of like the variability, which is not in terms of like available with us. So we are assuming that that is causing this. So that is the like the original idea of the Z part, and that's why it says unknown noise Z.
Got it.
Now, while we are fitting the model, uh, we usually try to minimize something, right? In this case, we are minimizing the sum of squares. We could have done something else. Uh, So like for example, instead of square, you can do fourth power or something, some other good function of it. But when you are doing that, you are making two assumptions. One is that the model is really linear because we are doing linear model. And second is among the all possible linear models, meaning among the all possible beta or theta, whatever parameter that is possible, we are choosing the one that is minimizing the sum of squares.
Yes.
Okay. That theta may not be, it might be true that the model is truly linear, but this theta is not the real theta. It was slightly different. Okay. But since we have no way of knowing that, we have to do like we have to find the best fit by minimizing something,
Right.
by choosing some objective function. So we have chosen this. This is like one of the good candidates, you would say.
Right.
So once you have done that, you get some estimate of theta, and for that estimate of theta, you get an estimate of the z also. So that's the error part. So this is error in the sense of if linear model were the true model and we try our best to fit the data to the model, then this is the part that is not fitted by the model.
Okay. Okay. That makes
Okay?
sense.
So in reality, you can think of it this way. So there are several sources of the difference. First difference is the z part, what is not explained by the theta, who explained by x at all. Like there are unknown sources of variability other than x. So that is never going to be contained in the model. Second is the true model may not be linear. So there will be some parts which is non-linear part that is again not going to be captured by my model because it's linear model. The third is even if the true model is linear, the theta that I am getting by doing the minimization work may not be the true theta.
Okay, that third one that you're saying, that to
Yes.
me sounds like the error part of,
That is like the contributor of the error part. But once you are fitting a model, you have no way of knowing which one is which because
oh,
you don't know the true
oh,
model
so we
and you
just
don't
call it
the
noise. We just call it
yeah,
noise.
all is getting mixed. So all of that together is getting. So remember that there are these multiple stages of error sources, but our data doesn't have enough information to know all of this. So we get a single estimate of what we are calling error.
Got it. Okay. Okay.
That's the full summary.
That makes a lot of sense. That makes a lot of sense. Okay. That was one of the main questions we had.
Yeah,
Um,
and also always remember to in our classes we used to follow a notation that unknown things or parameters are Greek letters and the known things are Roman letters or English letters. So you use E and epsilon to
yes.
just keep the difference in mind.
Okay. Yes. That makes sense too. I remembered that. Okay, buddy. So that was the regression slides. I think we tracked pretty
Yeah, I
well.
think we have mostly covered a lot of stuff.
Let me close this
I
one.
will just quickly add one more statement.
Yes.
We didn't cover the other kind of loss functions. So remember we said that we are choosing the sum of squares and L1 norm. And the funny thing is If you choose L1 norm and suppose you have 50 data points or something, then what L1 norm minimization does is it looks for all the points between all the lines between pairs of points. So like if you have suppose you have 50 points, let's say we are regressing with only one variable. So you have a scatter plot of 50 points, right? Just imagine it in your mind. And between any 2 points, I can draw a straight line.
Yes.
So it will be 50 choose to many straight lines that are possible.
Oh, okay.
Some
Okay.
of them might be similar, is like possible, right? And it turns out the L1 norm always chooses one of them. It's always one of the line that passes through two of the points.
Whoa. Oh, I guess that makes sense. What's been minimized then out of like how does
Minimize the sum of absolutes of over all the possible, all the data points, like all 50.
okay.
But it turns out the final solution includes exactly two of them.
Wow. Okay.
As if the other points don't matter. As if like just by passing through these two specific points, it is minimizer of the over all the 50 points.
Got it.
And that 50 can be much larger number also. It doesn't matter.
That's super cool. That's super
Yeah,
cool.
that's a cool
What,
method. It has a proof slightly complicated, but it just turns out to be like this.
when do we use this method?
It's not like you have to use this method, but just think about like when you do understand, say, mean versus median, you
Yeah,
know that the median is supposed to be more robust than the mean, right?
right.
And it is less affected by the extreme outliers.
Yes.
So in regression setup, also people like there is an area of study like robust regression, because regression, as we discussed, also is affected, linear least squares is affected by outliers.
Uh,
And we discussed the influence of a point and that kind of stuff. A single point can pull the line upwards or downwards a lot, depending on where it lies.
especially with the squares then too, right?
Yeah,
Yeah.
because of the squares. So L1 norm is one way of getting rid of the square. So no point is to like really influence it. So this is like the median counterpart in the regression setup,
I like that comparison then too. That makes sense.
because median also is like it's not affected by outliers beyond a certain point.
Right. Yeah. Okay. Got it. Can I open this one to go through here? Let me see. Convex.
Before that, I'll take a 2 minute break.
Yes. Oh, this one's only 4 pages. 2 pages? Oh my God.
Hi.
Hey, Sajay.
Hi.
Um,
So this is about convex optimization.
Yeah, this is honestly where it stops making sense. I think at a basic level, I understand how to define a convex set mathematically and what this
So basically,
image
the two
means.
points that join a line, it should be inside.
Exactly. So conceptually, I understand it, but once we get to the math, I'm not very familiar. Like
Okay.
I think starting from this page, it starts getting very confusing.
Okay. This is like a linear algebra.
And then it goes into gradient descent, which is a big topic that we did
Yes. That's
on
the main topic.
Thursday.
So gradient descent as a optimization method is very good when it works, and convexity is a good candidate of, well, we know if the situation is convex in certain sense, then it works.
Hmm.
So let's start with the part above, the convex basis part. Yeah. So let's start with this. The before definition two, there are three examples. Let's go through them first. So just the bottom of the first page.
Bottom of the first page.
Yeah. So we understand the definition well, right? If you take the condition for convex is, if you take any two points and join them by a line, it should be inside the set.
What is theta? Theta
Theta
is
is any number between 0 and 1.
okay.
So how do you describe a line segment joining two points? Is you take some weighted average of the 2 points. So like I take 25% of X and 75% of Y, or I take 70% of X and 30% of Y. So if as you vary that theta, you get the linear line segment between X and Y. So this is the geometry part of it.
How is that a line? I'm sorry, give me 1 second.
Yeah, just think about it. So you have, let's say, 2 points, X and Y, which are the two endpoints of the line segment. And
Okay.
then you are taking different weighted averages of these 2 points. That will give you the whole line segment joining them.
Okay. Okay. Got it.
Okay.
Yes.
That's
Yes.
like the geometry of it.
Okay.
In fact, that's how people define line segments also.
Okay.
And then this statement is saying that the whole line segment should be inside the
Y-
set.
Yes.
Okay. So the set on the left, you can take any 2 points on it and join the line segment. It should be totally inside.
Contained.
Okay. In particular, if you take any sphere or even ellipse kind of thing, those will be convex.
Yes.
And any triangle is also convex in 2 dimensions.
Yes.
Squares and rectangles are also convex.
Yes.
But pentagons may not, even quadrilateral, some quadrilaterals may not be convex.
Yes. Because they could have an
Because
inside
it can
shape.
have an angle kind of thing.
Yeah.
So in general, for a polygon, if there is an internal angle which is more than 180 degree, then
Mhm.
it's not convex.
Yeah. That makes sense.
So that's like the geometric picture you have in mind.
Yes.
And in higher dimension, these things are not as easy to describe because higher dimension angle itself is difficult to describe.
Yeah.
So, but some simple things can be done. So, for example, subspaces are always convex. Subspaces like in 3 dimension, a plane is a subspace. A plane is always convex
Got it.
because you need 2 points on a plane. If you join, you will lie on the plane.
Yes.
And then spheres in higher dimension also make sense.
Can I ask one question there though? In a plane,
Mhm.
oh, hello? What happened?
Yeah,
Oh. In a plane though, it implies maybe like an infinite space. Can
yeah,
an infinite space also be convex then?
yeah. Infinite spaces can be convex very
Okay.
much. So convexity doesn't have any restriction on finite infinite.
Okay,
It
cool.
works.
Got it. Oh yeah, because it's still contained inside. It still follows that definition then.
Yeah,
Yeah. Okay, that
yes.
makes sense.
Okay. And if you scroll down a little bit, there are more examples. So I think, yeah. So affine spaces are basically you take the plane and then you move a little bit up and down. Okay.
That makes sense.
And half spaces, does this definition make any sense to you?
I guess you take a subspace and it's half of that maybe.
No. So I'll describe what is happening. So what it is doing is you take the point A,
Okay.
and what it's saying, telling me to do is take all points X such that the dot product is less equal to something. Okay? Now that's very difficult to imagine. So let's think of this way. Let's say instead of less equal to, I do exact equal to. So A dot X equal to B.
Okay.
Okay. Now that will describe, that is basically summation AI xi equals B.
Yes.
So that's like equation of a plane.
Yes.
Just like in two-dimension equation of a line is A1 x1 plus A2 x2 equals something.
Yes.
Ax plus by equals C.
Yes.
In two dimensions, that's the equation of a line. In higher dimensions, the corresponding thing of line is plane.
Got
So
it.
if instead of less equal to, you put equal to, then you get a line or a plane. And half space basically is everything either on the plane plus either above or below, depending on whether you're putting greater equal to or less equal to. So everything on one side of the plane, you are including, the other side you are excluding.
Okay. Okay.
And that is convex.
Got it.
So in two dimension, you can imagine you draw a line and then everything which is below the line
Is a half space.
is a half space.
Got it.
So you can literally think of it half, right? Half of the plane is covered, half of the plane is not covered.
Why is it only
You have two
less than?
sides.
Why can't it be greater than as
Yeah,
well?
it can be greater equal to also. You can choose other side, either way.
Okay.
But if it's greater equal to, you can put a minus n and do less equal to that kind of things.
Oh, duh. Yeah. Okay. Got it. Okay. Wow. What
Okay.
we were doing. So this is the depth. Oh, these are
So those are,
examples. Intersections
yeah,
of.
these are examples. So it's good to have some examples in mind when people are talking about these abstract definitions.
Yes.
Okay. And then the second definition is saying, if you give me some finite collection of points, and then I can do some all kind of linear combination things and get a convex subset out of it. Now,
Like,
what this will do is, let's imagine only 3 points.
okay.
Okay. Then what this will do is, between 3 points, I will join the 3 line segments, joining them to get a triangle.
Yes.
Sorry. And this will give me all the points inside the triangle.
Yes.
Okay. For 4 points, it will draw a quadrilateral,
Yes.
and it will give me everything inside the quadrilateral, with the understanding that in case a quadrilateral was non-convex, then you basically get a triangle.
You
If you
base
want, I can draw some pictures, but you can imagine also.
you basically get a triangle. I lost you there.
Yes. Is there a way I can draw a picture while you can see?
Oh.
Can you see I'm drawing a triangle, green color on the left?
Yes, I can see.
Okay, very good. So now suppose my original quadrilateral is this.
Yes.
Okay. Then what will happen is it will draw this line also, because it is one of the 2 points. Like I'm joining one of the two vertices, I'll get this extra,
Right.
and then it will do the whole area.
Oh. Whoa. Wow.
Okay.
Okay.
Then your net result is a triangle instead of a quadrilateral,
That
even
keeps,
though you have 4 points. So basically, these 3 points is giving you the triangle, and the fourth point is inside, so it is not doing anything.
yes.
Okay?
Yes.
So when you do this kind of thing, this is called the convex hull.
What is it called?
Convex hull, HULL hull.
Okay. Oh, convex. Okay. Hull. Okay. Got it.
Yeah.
Okay. Hull. It's a new word.
So that's like a good way of generating a convex set. If you give some 5, 7 points, I can do the convex hull of all those points and you get a convex set.
Yeah, this keeps working in more and
This
more.
is working in any number of points, any number of dimensions. And also, this is a good way of checking if a set is convex. Like you can say this is the convex hull of these 3 points or these many points. Then I know automatically it's a convex set.
Got it. Okay.
Okay.
Okay. Very
Move
cool.
on.
That's actually pretty cool. That's crazy that now geometry is becoming a part
Yeah,
of.
yeah. Convexity is geometry. Convexity is not
Yeah,
about
please
other
do
things.
check.
But
Yes.
yeah.
Yes. I think it's easy. It doesn't have to be though, right? Like I think it's just easier to visualize, but I know what you mean, right? Like there's we can do this all without even drawing shapes, right? Like if we
Yeah, but like the ideas are coming from
the
geometry, so it's
ideas.
easy to understand if you know the geometry.
Yes, yes, that makes sense. Okay, so that definition checks out combination that is defined by a set, convex hull, L1. What is the L1 norm ball?
So it's a ball. So you know the different norms have different definition of like what a set would be, right? Like so under any norm, if you define a set which is like set of all points under that norm with norm less equal to some constant r, that's called a ball for that norm. Because for two norm, if you define like norm of x less equal to r, that's a ball of radius r. You agree to that?
Oh,
In Euclidean norm, like norm of x is just the length of x. Now, if I say the length of x is less equal to r, that's a ball of radius r.
norm of x less than r is a ball of radius r.
Yes.
Do you mean like a ball, like a sphere?
Yes. In three dimension, it's a sphere. In two dimension, it's a circle. You agree to that? Like norm of x less equal to 1 in two dimension is a circle.
How is that a circle, Sujay?
So let me draw it down. So, this is x, and we're doing norm, right? Less equal to r. Now, what is the formula for norm? Square root of x1 square plus x2 square, right?
Yeah.
Sorry, try to write
The
that.
L2 norm is that.
Yes. Yeah, I was talking about L2 norm in particular. For
Oh,
L2 norm, do you
you
agree?
just change it. Okay, the dimension of that ball is changing then.
Yes. So in other time, like for all other p, it's not a ball. It doesn't look like a ball, but we call it a ball.
Oh, I get it. I get exactly what you're saying. Okay, so L7 norm, if you're doing that, it's called a
Yeah,
ball.
it looks something else.
That's
So
why
I'll
you
draw.
the dimension.
So for L2 norm, the ball looks like this circle.
Oh gosh. Okay.
Okay.
Yeah.
For L1 norm, it looks like this. Looks
I
like a
get
square, but it's a ball.
Can you draw me the seventh
For
dimension today? Yeah.
Yeah, I draw the seventh dimension also as quickly as I can. So seventh dimension will look like this. Okay. So by the time you go to high dimensions, it will almost look like a square, but the corners will be a little bit rounded. And
Oh.
if you do infinite norm, the corners will be exactly straight, so it will be exactly square. But
Oh,
it's not so the one norm is like a rotated square. This is like a proper square.
got it. Got it. Got it. Got it. Okay, this makes sense. This
Okay.
makes sense.
So
Okay,
this is how all the balls look like.
got it. And this is
And
called
only one of them looks like the ball in our usual set.
yes. Okay.
So the idea is that all these balls are convex.
Yes. But it doesn't have to be that. It's just saying that that is convex.